Don't know. Okay.
All right, let's take a look at 189. We're going to start our next section today. It's going to be a continuation of this rational root theorem that we were doing yesterday, but we're going to extend it a little bit to help us find additional x-intercepts. When I say rational root theorem, do we know what the word rational means? If you were to take, it can be divided, aka a fraction, okay? So we essentially have two types of real roots. Real means graphable, like the ones you can actually see on your calculator. So when you look at your calculator and you're able to pinpoint where some x-intercepts are, they're either going to be rational, meaning there'll be some type of fraction. Whole numbers are fractions too, by the way, you just put them over 1. But then you could have a different type of x-intercept that's not a fraction or not rational. For instance, pi, 3.14, what is it, 15? No, there's a 9 in there. 3.1415, 992 something. 9265? Okay, so that's pi. You could have the square root of 2. That's 1.4 something. Okay, you cannot represent that as a fraction. So we either have rational, meaning fractional x-intercepts, or other ones that cannot be fractions. Do you know what those are called? If they're not rational? Irrational. Good. Okay, like pi, square root of 2, could be other things. All right, so before we actually, oh no, did it break?
Yeah.
Oh,
We'll fix it.
they'll fix it. Okay, they're decorating my door out there. I think they're.
Did you see the Roach Express?
The Roach Express.
Yeah.
No, I'll have to go over and see it. Did you decorate it? Yeah. Okay. What?
There's another picture there.
Uh-oh.
I don't know what it is.
I'll have to go see it. The candy cane wreath that they made, I guess it fell off the door. Oh well. Okay, before we actually get into kind of how we can extend this rational root theorem, I just want to practice identifying some characteristics that we've been dealing with graphs up to this point. So they're giving us a function at the top, and they provide the graph to us, so we don't really have to use our calculator to help us get a picture of it. Can we try to pick apart 3 characteristics or 3 things as to why this equation and this graph make sense together? Like how we know this equation would produce this graph? What do you see?
The highest is x to the 4th, and it goes through the x 4 times.
Okay, 1, 2, 3, 4, all with multiplicities of 4. Okay, so degree equals 4, and multiplicities add to 4. I like it. Can we find 2 more reasons as to why this equation would produce this graph? Do you see one, Eli?
It would be the right side rises, and you can tell by the end of the equation that it's a positive.
What's positive?
The 9.
Ooh, the 9 tells us something else. It's not the fact that this one's positive. Yeah? The leading coefficient. So that 3 is positive. All right, so both sides rise because the leading coefficient is positive and degree is even. We already said the degree was 4. So both sides should have the same end behavior because the degree is even. Looks good. Speaking of that 9 that Eli mentioned earlier, can we take a look at that one? Yeah?
The y-intercept is at 9.
The y-intercept is 9. Okay, so constant term equals y-intercept. Those match. Good. Okay. I like those. So what conclusion can you make specifically about the 4 x-intercepts of the function? I'm going to kind of lead you into this because this question might be a little bit vague. Remember when we did the whole chart analysis, like positive, negative, 0, imaginary? Can we take a look at this graph and determine the exact combination that we have? How many positive, how many negative, how many 0, how many imaginary?
We have 2 positive, 2 negative, 0, 0, even 0 imaginary.
All right, so 2 positive, 2 negative. We're already at our max of 4 based on our degree. So we have 0 at the origin and 0 imaginary. Looks good. Okay, so now that we have this analysis, at least specifically about the x-intercepts, let's go ahead and use the rational root theorem from yesterday to actually figure out the exact locations of those x-intercepts. All right, so can we develop a list of all the possible fractional x-intercepts? How did we create that list of like plus or minus numbers from yesterday? Go ahead, Eli.
You take the constant term and you divide it by, like you find what all multiplies up into that, and you divide that by the 3x over 4, since that's like the highest multiplication.
The highest power. Okay, so we're going to take factors of 9, that constant term, and divide them by factors of the leading coefficient, which would be 3. So factors of 9, plus or minus 1, plus or minus 3, plus or minus 9. And then factors of 3, thank you ladies, plus or minus 1 and plus or minus 3. All right, let's make our list. So 1 divided by 1, 1 divided by 3. 3 divided by 1, 3 divided by 3 is already listed. 9 divided by 1, and then 9 divided by 3 is already listed. So 4 times 2, we have 8 possibilities, okay, not as big or as many as the ones that we saw yesterday. So now that we have the graph given to us, can we reason through as to, out of all these 8, can we pick the ones that we should actually check and verify using synthetic division? Do any of the x-intercepts in the picture look like the possible ones in our list? Go ahead, Eli.
Plus or minus
3. Okay, so we have a positive 3. We'll circle that one. Caitlin, did you have another one? You were going to say 3 as well. Okay. Do we have a plus or minus 1? Yeah? I'd agree with a third. Okay, something right there. We definitely don't go through positive or negative 1, and we definitely don't go through positive or negative 9. So I think those two match what we have in there. So notice what's happening here. We can physically see all 4 x-intercepts. Okay, they're graphable, bless you. So if they're graphable, we know they're either going to be fractional x-intercepts or irrational x-intercepts. The problem is only 2 of them actually come from this fractional list that we develop. So what do you think the other 2 must be? Irrational, okay? One of these, like a square root of 2, a square root of 10, probably not a pi, okay, but some number that you can't write as a fraction. So let's go ahead and verify these first, and then we'll try to find those irrational ones. Let's go ahead and use 3. I got 0. Alright, so 3 definitely works. The other one we said we should check was negative 1/3. I forget, did we talk about yesterday how you can use the quotient values? Or did we go back and use the same? Did we use the same coefficients yesterday, or did we use the quotient ones? We use the same ones? Okay. What we're going to try to do is use the quotient ones, because we know from when we did synthetic division earlier, if the divisor goes in evenly, the quotient should go in evenly as well. It's almost like if you did 8 divided by 2, you know how you would get 4. So not only 2 goes in evenly, but 4 would go in evenly as well. So just to save us an extra number, we'll go ahead and use 3, 1, -9, and -3. So instead of having 5 numbers to use, we'll just go ahead and use the 4. We'll see why we want to do that in a moment. All right, so we'll go through another division. Alright, looks like that one works too. Now, can we think about this? If we started with a degree of 4, okay, from the very top equation, and we divide it twice, can we think about what this leftover quotient would be as a function? Can we name it? Yeah? You're close. If you 3x squared, no x's, and then -9. So this is a quadratic function. Okay, we started with 4 and we divided by 2, so it makes sense that we have 2 left. Okay, quadratic function. So this is why I want to use the quotient values, because we're starting with an x to the 4th, but notice how we're dividing it and simplifying it down to a quadratic. Now, if this is a quotient piece from the synthetic division process, we know that this should go in evenly as well. So we can anticipate a remainder or an answer of 0. Can we solve for x? Add the 9, divide the 3, square root both sides. Don't forget the plus or minus. Square root of 3 is irrational. Okay, you cannot write it as a fraction. And check this out. If you were to type in square root of 3 on your calculator, you get 1.732. Does that kind of look like where the other 2 x-intercepts are located? Positive, negative, right? Okay, so what we're going to do is exactly what we did yesterday, but we're going to take it a step further. Instead of ending at the division, okay, verifying the x-intercepts, we're going to take a look at that leftover quotient and see if we can take that any further to find any other x-intercepts. For instance, irrational ones, or maybe even imaginary ones. So we'll go ahead and list all of the x-intercepts that we found for this function. From the rational root theorem, we confirmed 3 and -1/3. And then we took the quotient and solved that a little further, and we got positive square root of 3 and negative square root of 3. All right, so we found all 4 x-intercepts. Notice how 2 of them are positive and 2 of them are negative, just like we anticipated. None at the origin, none are imaginary. Okay, so can you see how what we're doing is just like what we did yesterday, just one extra thing. Okay, one extra analysis. Let's go ahead and try another one. Okay. So we have a function at the top, and they give us the graph. Is there something in this case, though, that really doesn't make sense between the equation they give us and the provided graph? Yeah?
The multiplicities don't add up to 4.
All right. Okay. So degree equals 4, but multiplicities add to what? 2. Okay? So with that observation, can we list how many positive x-intercepts we have, how many negative we should have, how many are at the origin, and then how many are imaginary? What do you think, Lucas?
1 negative, 1 positive,
And 2 imaginary. All right, so we can see the positive and negative from the graph. One's on the left-hand side, one's on the right. We definitely don't go through the origins, we'll put 0 there. And if our degree is 4, and we've only accounted for 2, we know the other 2 that we can't see, okay, not graphable ones, are imaginary. So in this rational root theorem analysis, we know we should get 1 positive and 1 negative answer, but then eventually we're going to figure out what the 2 imaginary ones would be. So let's see if we can do this. Let's develop our list of all the possible fractional x-intercepts. We're going to need factors of 4, or rather -4, divided by 2. So factors of 4 over factors of 2. Alright, let's list out all of our possibilities. Plus or minus 1, plus or minus 1/2, plus or minus 2, plus or minus 1's already listed, plus or minus 4, plus or minus 2 is already listed. Alright, so we have 8 possibilities. Looking at the graph, can we think about, of the 8 that we have, which ones we should try to check to see if they're x-intercepts? Go ahead, Marcus.
1 and -1.
1 and -1/2. Okay, so this looks like definitely 1, and this could be -1/2. We'll check it. So we're not going to worry about those 2. Let's go ahead and do our division to actually see if those values are x-intercepts. All right, so we'll test 1. Looks like that one works. Let's go ahead and try -1/2. Okay, we're going to take the quotient values from the previous division, because now we'll just have 4 instead of the original 5. Looks like that one works as well. So can we think about, if we were to put the x's back into this final quotient piece, what the polynomial should be? We started with a quartic and we divided twice. Yeah.
2x squared plus 8.
There we go. 2x squared plus 8. So that would be a quadratic function. And if this is a quotient, because the remainder was 0 previously, we should anticipate that to go in evenly as well. So we'll set it equal to 0. Can we solve for x? Subtract the 8. Divide the 2. Oops. Square root both sides. Square root of -4. You can't, so it's not real. That means it's going to be imaginary. Square root of 4?
4i.
Not 4, close. 2i. Okay, square root of 4 is 2. Square root of a negative is imaginary. And notice how that matches what we anticipated. Okay, based off of our positive or negative, 0, imaginary options. 1 positive, 1 negative. We confirmed those from the rational root list that we developed. And when we took the quotient further, notice how we got 2 imaginary numbers, 1 positive and 1 negative. So we'll list the x-intercepts as positive 1, -1/2, and then positive 2i, -2i. We hanging in there? Yeah?
Are we having class before break?
A quiz. Okay, test will be out like a day or 2 after break. Okay? All right, let's go ahead and try another one. Consider the function at the top. Answer the following questions. Graph using a calculator and then sketch it to the right. Can you grab one? All right, there should be calculators around on the desks. If you don't have one, maybe try to find one or just work with a partner. Let's go ahead and graph it.
was 7 and 15.
All right, before we hit graph, let's go ahead and hit our window button. We're going to try to make up a window that makes sense to us. So if you look at the paper, because I want you to draw it on your notes anyway, the x's are going from -3 to +3 counting by ones. So I suggest putting that in your calculator for your window for the x's. The y's, on the other hand, are not listed, so that means we have to kind of come up with some y values that make sense. Can we think about looking at the equation and figuring what a possible y window would be so that we can see a certain point or certain places on this graph? Yeah? All right, this is your y-intercept. So you know your graph is crossing the y-axis at that spot. So let's make sure we can go down at least that far. So I went down to -15, okay, a little bit lower than -10. We really don't know how high the graph is going to go. Actually, we can't anticipate it, right? If we have an even degree and a positive leading coefficient, what's the end behavior going to look like? Both rising, all right? So the graph's going to go up forever. So I don't think it really matters how big the y value is, the y max. So this is what I had in there, but we can always go back and change it. Let's go ahead and hit graph. I say that's pretty good. Okay, so on the x-axis, we have an x-intercept roughly here, and another one roughly there. And maybe I'll label the y-axis at -10. So I'm going to go through right there. We're just drawing a rough sketch. So something like that. Looks good. Okay. So now that we have a picture, can we anticipate where these 4 roots should be located? Our degree was 4, so can we figure out the types of x-intercepts we have? Can we figure out how many positive, negative, at the origin, and imaginary? Yeah?
1 positive, 1 negative, and 2 imaginary.
2 imaginary, yep. 1 negative, 1 positive. Those are graphable. We can see them. That only brings us up to 2, though, so that means the 2 we can't see are imaginary. All right, so let's go ahead and actually figure out what these x-intercepts are. We're going to start with the rational root theorem. That's going to help us develop a list as to where the fractional ones are located. Let's see, we need factors of -10 divided by factors of 12. There's going to be a lot. Yeah, okay, we'll take our time. Remember, we're not actually going to divide it, okay? We're going to kind of reason through which ones make sense. 1 divided by 1, 1. 1 divided by 2, 1 divided by 3, 1 divided by 4, 1 divided by 6, 1 divided by 12. Moving on to 2. 2 divided by 1. 2 divided by 2, already listed. 2 divided by 3 is not. 2 divided by 4, already listed. 2 divided by 6, already listed. 2 divided by 12, already listed. So that one was nice. Move on to 5. We'll have 5, 5 over 2, 5 over 3, 5 over 6, 5 over 4, I skipped, by accident, and then 5 over 12. Alright, last one, moving on to 10. 10 over 1. 10 over 2, already listed. 10 over 3 is not. 10 over 6 already listed. 10 over 12 already listed. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 times 2. 32 possibilities. Okay, we're not going to do synthetic division 32 times to figure out which ones are the correct ones. Since we have a picture, let's go ahead and reason through as to which ones actually make sense for us to check. Can we think about it? Any of them kind of look like what they should be? Can we cross some off that clearly don't make sense? What do you think, Eli?
All the ones that are just even, 1, 2, 5, 10, all of those.
Alright, all the whole numbers definitely don't make sense. And actually, anything bigger than 1 wouldn't make sense, because we don't have anything bigger than 1 or kind of smaller than -1. So 1 over 2, 1 over 3, 1 over 4, 1 over 6, 1 over 12 are possibilities. 2 over 3 is smaller than 1. 5 over 2, not smaller than 1. 5 over 3, not smaller than 1. 5 over 6 is smaller than 1. 5 over 4 is bigger than 1. 5 over 12 is smaller than 1. 10 over 3, bigger than 1. So now we're down to 1, 2, 3, 4, 5, 6, 7, 8 possibilities times 2, 16. So we went from 32 to 16. Not bad. Bless you. Let's see. Let's go ahead and maybe utilize our calculator a little bit more. If you hit the trace button, try to get your cursor pretty close to one of them. Let's see. For the right one, I kind of bounced back and forth between it. So something between 0.64 and 0.7. Do we have a listed fraction that's somewhere in there? .64, 0.7, something in between. 2/3, okay, 0.666, definitely. And then let's go ahead and check the other one. Alright, I'm pretty close there. -0.255. Yeah? -1/4. Okay. So of the what, 8 that we had left, those 2 kind of make sense. So let's go ahead and check those. We'll do positive 2/3. Uh, 12 divided by 3 is 4, times 2 is 8. 27 divided by 3 is 9, times 2, 18. 66 divided by 3, 22, times 2, 44. Mm. 15 divided by 3, 5, times 2, 10. Looks like that one works. Alright, and the other one we want to check was -1/4. Quarter of 12. We got 3. Quarter of 22. Or sorry, 24. I got 6. And then a quarter of 60. I got 15. Looks like that one works too. All right, so the rational root theorem has just confirmed the positive x-intercept and the negative x-intercept that we saw on the graph. Now we got to take this quotient piece and try to figure out these two imaginary ones that are left. So if we started with the quadratic, not quadratic, I just gave it away. If we started with the quartic and divided twice, we should be left with a quadratic. So let's go ahead and put the x's back in here. We'll have 12x squared plus 24x plus 60. And somehow we want to solve if that is 0. So what do you want to try? Yeah? Let's, okay, GCF, we'll take out a 6. So 2x squared plus 4x plus 10. We could probably take 12 out. Yep, so if we take another 2 out, this would become a 1, this would become a 2, and this would become a 5. Alright, so we factored GCF. Can we keep factoring? Two numbers that multiply to 5 add to 2? No. So how can we solve for x? We can't solve by factoring, so is there something else we can try? Yeah? Mm-hmm.
Plus or minus b or
all over 2a. What's that called? Quadratic formula. We said this is a quadratic equation, so this is fair game. Okay, if we can't factor, quadratic formula. All right, now we're going to ignore the 12 because we already removed that. Okay, it's a GCF. So our A, B, and C are going to be the 1, 2, and 5. Easier numbers to work with. So x equals, we have opposite of b, so negative 2, plus or minus square root. B squared, so 2 squared would be 4. Then we got to subtract 4 times a times c. So 4 times 1 times 5. That would be 20. All over 2a, so 2 times 1 would be 2. 4 minus 20, negative 16. Can we figure out the square root of negative 16? The square root of 16 is 4, and square root of a negative, I. Alright, and if we're dividing by 2, notice how all the numbers are even, so we should technically be able to divide everything through. If we do negative 2 divided by 2, that'll be negative 1. And then if we do 4i divided by 2, that'll be 2i. So there are two imaginary numbers that we said should result, okay, based off of our positive, negative, origin, imaginary combinations. So let's go ahead and officially list these x-intercepts. We confirmed by the rational root theorem that 2/3 and negative 1/4 are graphable. Okay, we can see them. And then we took the quotient further to find, in this case, our imaginary ones. So we'll have negative 1 plus 2i, and the other one would be negative 1 minus 2i. Notice how they show up in pairs. Alright, so depending on what your resulting equation looks like, we can simply solve it, like the first two examples, but since this one was quadratic, factoring and the quadratic formula are up for grabs, okay, because there are different possibilities or techniques to solve when it's 0. We doing okay? We'll try a little bit more tomorrow?
Yeah,
Okay,
fine.
sounds good.
Auto flip.